So good afternoon and welcome to the final webinar in this series, Data Analysis for Biomedicine using Sigmaplot. And this week we're going to look at the final week's content, and I'll explain it very briefly and I'll take any questions that you have. So if you're listening, then submit questions through Google Hangouts via the Q&A option and I'll answer any questions you have. So while we're waiting for that any questions to roll in, what I'm going to do is I'm going to transfer you so you can see my screen, and we'll go through the content of week 6. This always just takes a little second just to make sure it goes right. All right. So when you get to the landing page of data analysis with Sigmaplot, you need to scroll all the way down to week 6 because that's where we're at. And you'll see that this week's content is the Chi-squared test and how to avoid bad statistics. So the Chi-squared test is different to the other tests you've met before because this is a test that's used to analyze data involving counts or proportions per category. And we'll explain what we mean by that more in the examples. We're also going to see some very recent publications from Nature and other leading journals saying that p-values can be extremely misleading and that it's important to interpret them in a way that is sophisticated. So let's click here to see the content. And as usual, you see the contents down the left-hand side here. I'm going to skip over the introductory video and we'll go straight to the experimental design. So in the first experimental design that you'll encounter, you have to imagine that you're counting the number of alpine hares and lowland hares that live in each of 3 Russian habitats, namely the tundra, the foothills, or the tree line. And what you want to discover is whether alpine hares and lowland hares are equally distributed across the 3 habitats, or whether they each prefer different habitats. And so one way of summarizing the data that you obtain would be in this table, which is called a contingency table. And it's just a summary of the data you got. So you can see there are 3 locations, tundra, foothills, and tree lines, and the 2 types of hare, lowland and alpine. So for example, 125 lowland hares were found in the tundra, 16 lowland hares were found in the foothills, and 6 lowland hares were found in the tree lines, and so on. So these are just counts in different categories. This is not what Sigmaplot calls data acquired using numeric values, although these are numbers. What these are counts in categories, and you can see that very clearly. Here are your categories, and these are the counts in those categories. So as it specifies here, note this isn't a table of means and, say, for example, standard deviations or standard errors. It's just a summary of the things you counted. So with this kind of data, it's not possible to generate means and error bars, so don't try. One other way you can represent this is what is called a stacked bar graph. And you can see here for lowland hares, the majority were found in the tundra, some were found in the foothills, and few were found in the tree line. This is a nice way of representing this data graphically. And so now we'd like to analyze this statistically to find out if, as we suspect, lowland hares prefer one type of habitat and alpine hares prefer a different habitat. Okay, so the first thing you need to learn is how to input the data. And if you were to click in this movie here, what you'd discover is that you can enter the data in the same way as we've seen already, as a contingency table, or you can just input them as a big old line of data, in this case, hundreds of cases. I prefer this summary table here because it's easier to enter and it's easier to check that you got the numbers right. Then in the next movie, you'll learn how to analyze this. You'll walk your way through the advisor wizard to discover what tests you should use. You'll discover that you should use the chi-squared test for this kind of data, and then it will ask you to input the data, which just involves clicking these 3 columns here. And then it will generate the output, and this video will tell you how to interpret your output. And in this video here, we'll see how to report your results. So in video 6, in page 6, again, we show the contingency table and the stacked bar graph, and we explain how you would report that result in a paper. On page 5, you'll also learn how to generate the stacked bar chart that you see below. And you can practice doing that using one of the example data sets in the file that we provide. Okay, so that's the chi-squared test, and that's the last test that you're going to encounter on this course. The very final part of the content is just to show examples of bad practice and how to interpret p-values. So one of the first things you'll discover on page 10 is this quote. It may surprise many scientists to discover that interpreting a study result from its p-value alone is spurious in all but the most highly powered design. And there's a really nice example of this in this paper from Halsey, and I've adapted it here to make it even clearer. So suppose that you actually measured heights of all the world's giraffes that have ever existed, millions and millions and millions of giraffes, and you plot them like this, and you discover that on average, female giraffes are a tiny bit taller than male giraffes. In this case, it's in this plot, the mean difference is 0.5, and in this case, the standard deviation is 1. So population B are the female giraffes, and population A are the male giraffes. So these are all the giraffes in the population that ever existed. Now, in practice, we can't sample all the giraffes that ever existed. This is just a thought experiment. In practice, what we do is we tend to sample smaller numbers of animals to see if there's a difference between here female and male giraffes. So suppose that you took a sample of 10 female and 10 male giraffes completely random, and you wanted to know if there was evidence that female giraffes were taller than male giraffes on average. Well, if you look in this simulation, what you discover from this first sample that you take is that female giraffes are a little bit taller than male giraffes, and this is significant. The p-value here is 0.005. So if you were only to do this experiment once with this set of 10 and 10 giraffes, you'd conclude that female giraffes are taller than male giraffes. However, if you repeat this, if you just draw another 10 animals at random from the male and female populations, the second time you do it, just because of random sampling, unluckily on this occasion, you don't see a significant difference. Then you do it again, and you still don't see a significant difference. And then you do it a fourth time, and now you see a trend towards a difference. The p-value is 0.09, but it's not significant. So what does this mean? Well, what this means is if you sample with small numbers from a population where there's a small effect size, sometimes you'll detect a difference and sometimes you won't. So the p-value is not very reliable when small samples are used. And the argument that is being made in this paper by Halsey et al. Is in lots of biology, we undersample our populations, and we often only do it once. And so you'll see a result in the literature with a p-value that looks very promising, and you see this effect size, and you conclude that female giraffes are taller than male giraffes. And in this case, you happen to be right. But suppose the paper actually had only done this experiment, and by unlucky random sampling, they found no difference. Well, they probably wouldn't even write the paper, so you'd never discover whether there's evidence for female giraffes being taller than male giraffes or not. So the message is really what we need to do is increase the number of animals or people that we sample from when we do science. Okay, so that's the main point in this article. The p-values by themselves can be misleading, especially if we only do the experiment once with low n. So then on page 11, we learn a little bit more about statistical power. What this means is you might be asking yourself, well, how many giraffes should we sample from to be confident whether or not female giraffes are taller than male giraffes? And there's a little text here to explain what power is when you do a sample size calculation. And in the next page, you learn how to do a sample size calculation with this kind of data. So you learn how to figure out how many animals to use in order to get a p-value that's more reliable. So the argument here again is it's important to sample adequately so that when you do a study, you have a good chance of drawing the correct conclusion from it. So here's a thought experiment. There's a little bit of text that you need to read. And then in page 13, there's a little video, and it tells you how to do a sample size calculation in Sigma plot. And it's actually really straightforward and very easy. And so that's the main message of this week's content. First of all, you'll learn how to do a chi-squared test. And then in the second half, you'll learn how to avoid bad statistics. You'll learn that the p-value by itself is often not very reliable, and the best way to improve its reliability, or one of the best ways, is to make sure that you generate large enough sample sizes before you carry out an analysis. So I hope you found the 6 weeks content useful. We'll be improving this content in the coming year, and any feedback you have will be gratefully received. So feel free to email me or to post content on the forums if you have suggestions for how to improve this. So thank you for participating and good luck with your course.